look at this. Again, this is part B of number 2 from the Squashing Fischer Projections worksheet that we started looking at yesterday. If you want to build a model, you can. I'm going to show you kind of how the rotation works without having a model, but I know the models helped as we were talking about in the plane of the paper and coming out of the page and into the page. And so for this, oh wait, this should say part B. I put part E on a separate slide, right? Part B of number 2 from the worksheet. So first thing it says is to squash the following wedge dash structures into Fischer projections and indicate your sight line. So remember we said our sight line is always from the bottom right. When you are squashing a wedge dash structure into a Fischer projection, you always have to make sure that the substituents that are in the plane of the paper, so the single lines, right, straight lines, are as far away from you as they can be. Which means F is already far away from me because when I'm looking from the bottom right. So here's where I'm going to be looking. I should always be looking between a wedge and a dash. So I should always be looking between a wedge and a dash. I am here, so I don't have to worry about rotating this side. However, on this side, I need the single line, what's in the plane of the paper, to be away from me. So what we need to do is we need to rotate this part of the molecule. Right? If you built a model, you're just spinning it. So you're just spinning it so that the way it's going to look, I'm just going to draw it over here, and I'm just going to kind of make it straight. Here's F, here's H, here's CH3, right? I didn't do anything to this side. I'm just like turning it so it's straight across. And I'm looking here. Right, there's that side. I didn't do anything to that. For this side, I need the OH to be as far away from me as it can. Because when I'm looking down here, the OH is still close to me. So I need the OH, what's in the plane of the paper, to be as far away from me as it can be. When I do that, all I'm doing is rotating this. So I'm taking this single bond here, and I'm just rotating it. When I rotate it to put the OH up at the top, that's going to swing these down as well. When you're rotating something, what's in the plane of the paper isn't changing in terms of single line or wedge or dash because it stays in the plane of the paper. But as I rotate it, what happens is this becomes a wedge, this becomes a dash because we're rotating it around. We can look at what it looks like with a model kit as well because when you rotate it, the CH3 that's going into the page is now coming out towards us. This ethyl group that was towards us as we rotate it now goes back into the page. So we have a wedge, that's CH3. We have a dash. So this CH2, CH3 is an ethyl group. Just to save some space throughout this, I'm just going to put ET for ethyl. Again, just to save space. So here is what we're looking at. Right, we're no longer worried about this, because I rotated it how I needed to put what's in the plane of the paper away from me. So now we're looking from the bottom right, and we're essentially taking this molecule and we're looking at it down this way. So the H is coming out towards us, this methyl is coming out towards us. This methyl is going back into the page, this ethyl is going back into the page. So as we look at that, for the original, that's what we have here. This is where whatever is on a wedge goes to the left. So as I'm looking down this bond, the hydrogen is the first thing that's to the left. So here we have hydrogen and methyl, CH3. And then as I continue looking down, right, the wedge goes on the left. So here's CH3. And then the ethyl, which is a dash, is on the right. What's in the plane of the paper is always on the top and the bottom. That's why we keep it in the plane. So fluorine is at the very top. And then the OH is down here at the very bottom. So there's the original. Biggest thing with Fischer projections is making sure that what's in the plane of the paper is as far away from us as it can be. So we have to rotate it to make sure that it's right? Both of the things that are in the plane are away from us. Now, before we draw the enantiomer and the diastereomers, let's look at the R and S. All right, so let's look at the R and S configuration for each stereocenter. So this carbon and this carbon. So R and S, we have to designate priority. So we have fluorine, carbon, carbon, and hydrogen. So fluorine is going to be the 1. So now we're between 2 carbons, this carbon and this carbon. So you look at what it's attached to. This carbon is only 3 H's. This carbon is connected to another carbon, an O, and another carbon. So this entire group down here is priority 2. Here's priority 3. Hydrogen is priority 4. Remember your arrow. You're drawing your arrow from 1 to 2 to 3. So 1 to 2 to 3. So turn to the left. And then check where your lowest priority group is. Remember when we draw this, when we're looking at the R and S, we're no longer looking at the wedges and the dashes up here. We're looking at the wedges and the dashes within the Fischer projection. So this H, this CH3, right, these are coming out toward us. So this is considered a wedge. Up here would be a dash. So when you're looking at the R and the S, if you have a Fischer projection like this, your hope is that the lowest priority is vertical. If it's not vertical, then you need to switch it. Right, so this is actually an R configuration. Then we can look at the same thing. I'll use a different color. We can look at the same thing for the R and S configuration down here. So the first priority would be this oxygen. So there's priority 1. Then we have this carbon, or this carbon. Right, this would actually be second priority because you look at what it's connected to next. Because if all 3 of these are C's, then you look at, okay, where's the first point of difference? Obviously, it's not the C, it's what it's connected to. This C is connected to another C, to an F, and to an H. This is just connected to another C and 2 H's. This is just 3 H's. So this is actually priority 2 as well. Ethyl is priority 3 because that carbon is connected to another carbon. In this case, methyl is the lowest priority group. Right? There's no hydrogen as a lowest priority group. In this case, it's methyl. So draw your arrow from 1 to 2 to 3. So turning to the right. But again, look where your lowest priority group is. Our lowest priority group is horizontal. That's like a wedge. Right? Which means you change the designation. So when you're looking at Fischer projections, in order to use the steering wheel, the lowest priority group needs to be vertical. If it's not, you switch the designation. If you're looking at a wedge dash structure and you're looking at stereocenters, then you're just looking at where's the lowest priority, what is it? If it's a dash, we're good to go. If it's a wedge, we flip it. So then if we look at the enantiomer, because then it wants us to draw the enantiomer and any diastereomers. So remember in enantiomer, I'm going to pretend like there's a mirror here. An enantiomer is a mirror image. So I'm going to put this dotted line. We're going to act like this is a mirror. And we're just going to draw the mirror image. So F is still on the top. OH is still on the bottom. All right, and then draw the mirror image. So draw the mirror image of those groups. Draw the mirror image of those groups. So if we draw the mirror image here, right, we have H3C, the methyl group's there, ethyl group is here, and then the H is here, and then another methyl group here. So all I did is I did the mirror image. Now if we think about the actual definition of an enantiomer, right, when we talked about the R and the S configurations, this is when you change both chiral centers. All right, so here we'll say change configuration of both chiral centers. That means you switch the groups. Centers. That just means we switched both of the groups, which we did, right? CH3 and H switch places. Ethyl and methyl switch places. When you exchange the groups, that changes the configuration. So we don't even need to prioritize and look at the, steering wheel, because we know that for an enantiomer, if this was R, now it's S. If it was S, now it's R. Because that's the definition of an enantiomer. That they just switch configurations of both chiral centers, and that's because we've exchanged the positions of the two groups. And then for diastereomers. So remember the definition as we were looking at R and S of diastereomers is that one chiral center changes. So only one chiral center changes. What that means is that you switch groups on one carbon. So you only switch groups on one carbon, which is why we have two possible diastereomers. The fluorine and the alcohol group are not going to change because those are in the plane of the page. So those are going to stay. When we talk about switching the groups, we're switching these. Now you only switch one at a time, because if I switch them both again, that goes back to the original. So if I look at the original here, to create a diastereomer, you switch the groups on a single carbon. So I'm going to start by switching the groups on this first carbon. So instead of H on the left, I'm going to put H on the right, and I'm going to put methyl on the left. Now before I even continue moving on, I now know that if this was R and I switched two substituents, now it's S. Because if you exchange two groups, you change the configuration. And then I'm going to leave the two on the second carbon alone, because we can only change one carbon at a time. So if I left it alone, it was S, it's still S. So notice how from the original to this first diastereomer, only one chiral center changed configuration. Then we can look at the second possible diastereomer. Well, again, we go back to the original. Now we're going to leave the first carbon alone. So it was R, it stays R. Now I'm going to change the groups on the second carbon. So here's ethyl, here's methyl. Well, if I exchange the two groups on that second carbon, it was an S configuration. Now it's R. So for both of these diastereomers, only one carbon switched configuration because I exchanged the groups on only one carbon. Did that help? Yes.
And this was kind of early on, but placing the F versus the OH on the top and bottom, I made the model and both are on top of that orientation from that angle. So how would you distinguish that?
So it's based on where you're looking. So since we're looking from the bottom right, the fluorine is technically what we see first. So it's on the top. Since the hydroxide, since the alcohol is farthest away from us, that's why it's at the bottom. Yep, good question. Any other questions on this example?